in the film. The advantages are that the added energy produces a much higher quality of film microstructure. The impact energy transferred to the lattice from each ion creates a local transient thermal spike, which helps the film atoms settle into the lowest energy sites, which a more ordered crystalline structure. And this is a basic mechanism. Shadowing is also reduced because low energy ions follow electric field lines to the surface and arrive at near normal angle of incidence. And the chamber impurities are easier to control in vacuum than in highly purified gases. I won't go into that, but it's generally true. There are some indications that deposition at multiple energies can also produce better films than a single energy, but this hasn't been explored yet in detail. There are some papers available showing this in other materials. The Rome group has done some work with this in niobium, but I think it's very early. And that adding energy to condensing niobium ions produces a better film structure with higher RRR is well established in both simulation and in literature. It's been demonstrated in many places, including JLab. At JLab, it's been seen with ECR films showing a decrease in RRR with decreasing ion energy. The same film growth modes can be used with energetic condensation. That is the fiber structure and the heteroaptaxial deposition. With fiber growth, there are a few additional features that are really interesting. Instead of using an oxide to avoid epitaxy, you can use a brief period of ion implantation at very high energies to create a graded interface, resulting in an amorphous layer of niobium, having a very high shear strength. This is called ion stitching. It's nothing new. Andre has done this and his collaborators many times at Berkeley. And the potential advantage of this, it will support much thicker films. Shear stress builds up as the film gets thicker. And peeling won't be a problem with the thicker films, and this might be very useful if the defect density doesn't saturate with increasing film thickness. So by the time you reach the RF surface, you can even achieve a better RRR. After nucleation at the substrate surface, grain competition, in the case of fiber growth, will occur during grain growth, with the grain having the lowest surface energy predominating. And in the case of niobium, that would be the 110 plane surface. An advantage of this, a potential advantage of this, is that it will avoid surface roughening due to preferential sputtering by the incoming ion beam according to the differing surface energies of each. For this mode to be useful, the fiber width can't be too small, such that the grain boundary scattering dominates the electronic mean free path. The density of nucleation sites at the substrate needs to be understood and controlled in order to attempt to get a larger grain size. It is interesting, though, if the grain size is of the order of 0.2 of a micron only, and the grain boundaries were completely opaque to electron transmission, which they are not, we would expect a RRR on the order of 100 if no other defects were present. So this is a potentially viable film structure. A value of 100 is would have only a very slight impact on depressing HC1. We might expect the triple R value through the film from substrate to the final thickness to look like the red and blue curves in the graph shown here. The blue curve represents a defect density saturating fairly quickly with film thickness, as opposed to the red curve. And the asymptotic value of the blue curve represents the best value obtainable for that particular ion energy. And for different ion energies, there'll be, you would expect a family of similar curves with different asymptotic values of triple R. With energy, it's interesting. Again, this curves means nothing. It's an artist's conception, let's say. But you know that in the two limits, at very low energies, you get a very poor film structure. So the asymptote in the previous graph, if we plot on this axis, this is the saturated, or this is, let's say, the triple R, or electron mean free path, at the penetration depth. At very low energies, we know it's going to go to a very low value. I'm sorry,
No,
am I running on time? Okay.
We were discussing about the data with one of my Phillips.
Oh, I see. Okay. And it's good to look at extreme limits. And at the very high end, at high energies, you really damage the lattice. You destroy it pretty badly. So what that means is that there's a peak somewhere, and of course one of the goals is going to be to find that peak. And I'm going to go back just for a second. Does this go back? Oh yeah. If you were to make a third axis here and plot energy out this way, out of the board, you would see this asymptote start down close to this line somewhere, and if I do a little hand waving, come up to its peak value here, and as energy increase, come back down again. So if you imagine that three-dimensional surface, ideally you want to find the center of that. Another complication is, however, that at different substrate temperatures, we already know that there wouldn't be one three-dimensional surface. There would be probably a set of nesting surfaces. So that's another axis you need to explore. And those statements are kind of obvious. Go ahead, Intu. Yeah. What? Oh, 5 minutes? Okay. Okay. Primary focus at JLab is to understand the relationship between deposition process, film microstructure, and RF performance. That's been the goal from the beginning. Activities are largely organized toward reliably producing clean films, and using RF measurement ultimately as a metric, and carried out with a small group of collaborating universities. And I'll just mention this briefly. These things will be discussed later in talks in great detail by Andre Valent, Feliciano, Josh Bradlin, and Krish Mahadevan. Anyway, a large array of samples have been produced with the niobium ion deposition in vacuum, and this is to begin looking at points on these surfaces to try to, you don't want to measure the whole surface, it's too much work. You kind of have to find out where that maximum line is, and then look at the other axes as well in some clever fashion. The defect densities have been measured, again, the whole film thickness with values as high as 213. The film texture and microstructural properties have been measured using EBSD and X-ray diffraction. Triple R values as high as 114 have been achieved on highly mismatched surfaces. And again, in that case, you don't know how the defect density changes through the film. It's not surprising that it's lower. And the other interesting thing that they are doing, and I don't know whether this is discussed in the papers coming up or not, but films are being deposited on single crystal copper substrates of different orientations to mimic what you'd see in a real substrate, polycrystalline copper, to be able to actually examine and measure what happens with different grain energies, different grain faces rather exposed, and different grain energies, of course, surface energies. Initial emphasis has been on heteroaptaxial films on clean surfaces, but I already said what I said about fiber growth. I won't say any more.
Just a left button.
No, I keep thinking I'm pushing the laser. This we here means really the international community, because these things are being done at this laboratory, at INFN in Rome and elsewhere, and starting again at CERN, which would be very fascinating. It's, I think, the major problem that needs to be addressed, because if there are other issues besides the HC1 and the other, the effect of the energy gap mentioned by Alex earlier, you won't see them until this is out of the way, because this is clearly an influence that's fairly strong. Thank you.